Hello everyone, and welcome to this video on simplifying expressions of this specific form. It's the nth root, right, or the principal nth root of a to the nth power, right? So some expression, some number to the nth power inside the radical symbol, or as the radicand. And notice here that this, a to the nth power, the exponent, the power in here is exactly the same as the index of the radical. So keep that in mind. Alright, so in this video I'm going to discuss what this means, what's being asked of you when you see this symbolism, and then go over several examples. So let's begin. Alright, so in previous videos on roots that I've put up, we've talked about this symbol here, right? The radical symbol, and the number in here that's usually written in this little V area is called the index, and then the expression inside is called the radicand. I've written all this up in previous videos, so I'm not going to write it all here. And what we're looking at today in this video is the nth root of, and then some expression, some number represented by the letter a here, to the nth power, right, as the radicand, right? And this nth power, again, this is the same number as the index, right? So an example of something that looks like this, just some examples off to the side here, what would be the square root of 5 squared, or what would be the cube root, remember the 3 in the index, of say -7 to the 3rd power, or the 4th root, 4 in the index, of, and then -2 to the 4th power, and so on. All right. Okay, so very often people like to make the mistake of saying this. So again, don't just do this. I'll put a big don't down here. Do not just do this. Don't just undo them. Right? Very often people tend to say, hey, I'm taking the nth root of some expression to the nth power as the radicand, and you think, oh, this is the nth root. Inside here I'm raising to the nth power. Those just undo one another, and I'm left with just a. All right. I'll make a big point here. This is not always the case. All right. Sometimes it is, but this is not always true. All right, so we have to think about when it is and when it isn't. So don't just undo the power in the radical. Think, oh, a to the nth power is equal to a to the nth power, and that's true. But when you see this symbol, it means something. All right, it means something. You're not just finding any old root, but what's called the principal nth root. All right, so I'm going to break this up into 2 parts, like I did in the last video on evaluating nth roots. We'll talk about one case where n is even. All right, so what I like to call even roots. All right, so the index, right, the number in that little crook here, is an even number, right? So index equals 2 or 4 or 6 or 8 or so on. And also remember, when the index is 2, it's usually not written like this is the square root or the second root. All right, so hopefully you recall this from my last video. I'll write it here again a little bit here. When you see this symbol, around some expression, right, I'll use capital A here instead of lowercase a to the nth. What you're being asked for, right, again, n is even, 2, 4, 6, 8, all right, 10, 12, and so on. Every non-negative number, right, every positive real number has two even roots, has two square roots, has two fourth roots, two sixth roots, etc., and one positive root and one negative root. What you're asked for when you see this symbol is the non-negative root. The non-negative root, nth root of A. Okay, that is huge. All right. And of course, we talked about again in the last video, when you're taking even roots, all right, the number A, right, the radicand has to be non-negative also. So when you're taking the square root, fourth root, sixth root, eighth root, etc., the number inside has to be non-negative, and also the number you get, the resulting number, is also going to be non-negative. All right, and as a quick example of this, all right, so remember the square root of 4, an even root, even index. You're just thinking of what number can I raise to the second power to get 4? And it's got to be the non-negative one. I know, right? I know that negative 2 to the second power, negative 2 times negative 2 is positive 4. Negative 2 is the negative square root of 4. What you are asked for here is the non-negative. When you see this symbol and it's an even index, they want the non-negative root, right? So that'd be positive 2. All right, the fourth root, all right, say the fourth root of 81. Again, if you see an even index, you better have a non-negative radicand. If the number inside is negative, then you have something that's not real. Again, mentioned in the last video. Please watch my video on evaluating nth roots. But this would be 3, right? I know, right? I know that negative 3 to the fourth power is also positive 81. But when you see this symbol, I'll say it a bunch of times, when you see this symbol with an even index, what's being asked for is the non-negative nth root, not the negative one. Okay, so, and I'm going to stick with even roots here for a second. So when we see an expression like this, and n is even, all right, let's take a look at expressions like the title in the title of the video, the nth root of something to the nth power inside. Let's see what what's going to be happening when n is even. So again, I'm still talking here about even roots. All right, so this is still even roots. And for example, what's the square root of 5 squared? All right. Well, remember, when you see this symbol, your final result, your resulting number, is going to be a non-negative number, not negative, right? So what's a number that I can raise to the second power to be equal to 5 to the second power? Well, that would just be 5, right? And think about what 5 squared is, right? What's 5 squared? It's 25, 5 times 5. And then what's the non-negative square root, right? This symbol, what's the non-negative square root of 25? That's positive 5, right? Since 5 to the second power is 25. All right, well, look at this. What about the square root of negative 5 squared? Again, people tend to make a mistake when there's an even index, an even power in here, right? This is technically an index of 2 and a power of 2 in here. Very often people will just, oh, these undo each other, and I'm left with negative 5. But remember what I said up here. When you see this symbol, I'll say it again, and again. When you see this symbol and the index is even, 2, 4, 6, 8, 10, and so on, what your resulting number is better be non-negative. Right? So don't write negative 5. This is not negative 5. Again, just think about what what negative 5 squared is, right? That's negative 5 times negative 5, which is positive 25, right? A negative times a negative is a positive. And I get exactly the same thing as I did up here. And what is, I see this symbol. What is the non-negative square root of 25? That'd be positive 5. All right. So we're seeing that the square root of 5 squared, yeah, there you could say they undo each other and you're just left with 5 because 5 is non-negative. Great. But if the base on the power in here in the radicand, if the base is negative, yeah, you can undo them, but then you take the opposite. Or just, make it positive. And another way, we can make things positive is by taking the absolute value. All right, the absolute value of a positive number is itself. The absolute value of a negative number is the opposite of itself. So when we see the square root of some number squared, you can start off undoing those, say this is a, but just in case this is a negative number, we'll say, hey, let's ensure that it's non-negative by taking the absolute value. All right, so remember these symbols here, this is the absolute value of a. Okay, and that's key. And this is going to be the same rule. I'm going to do the same thing for every one of these even roots. All right, so here's another one, another couple. What would be the fourth root? And remember, this symbol means the non-negative fourth root, or the principal fourth root. What would be the fourth root of 5 to the fourth power? I'll just use 5 again. Right? Well, that's a positive base there, so what you're going to see is that these fourth root and fourth power will just undo each other. I'll end up with 5. All right, but let's go through this. This is the fourth root, the principal fourth root, the non-negative fourth root of 5 to the fourth is 625. And then what you're thinking of is what's the non-negative number that when raised to the fourth power would give me 625, and that is positive 5. 5 to the fourth power, 5 times 5 times 5 times 5 is indeed 625. You can check that out on your own. So you see when the base is positive in here and you got the same power in here as the index, those will just really undo each other and you're left with the base, left with 5. But when the base is negative, right, so here's another even root, same thing. Let's take the fourth root of, and then instead of 5 to the fourth, negative 5 to the fourth power. All right, and again, people make too many times, I've seen this, people make the mistake of just undoing these, the fourth root and fourth power undo each other, and they write negative 5. Remember, when you see this symbol with an even index, the 4 there is even, your final result needs to be a non-negative number, the non-negative fourth root of this number in here. So you could say negative 5 and then again take the absolute value, make it positive 5. We're going to see that this is positive 5 when I actually go through this, right? So this is equal to the fourth root of, and then what is negative 5 to the fourth? Negative 5 times negative 5 times negative 5 times negative 5. Well, any negative number to an even power, negative to the fourth here is a positive number. That would be positive 625 again, and I get exactly the same thing as up here. What's the non-negative number that when raised to the fourth gives me 625? That is positive 5. So you're seeing when the base is, when you have the the index is the same as the power, and they're even. When the base is positive, they just undo each other basically. When the base is negative, you do the opposite, right? To make sure that it's non-negative. Your final result had better be non-negative whenever you see this symbol, this radical symbol with an even index. All right, so I'm seeing here that the fourth root of some number to the fourth power is just like my square root rule. I can, I'll start off undoing them, say a, but whoa, what if a is negative? That can't be true if a is negative. So just to ensure that we have a non-negative result, I'm putting an absolute value symbols around that. It's the absolute value of whatever number a represents. And this is going to be the case in general for your even roots, okay? So in general, still talking about even roots here. The nth root, okay, the nth root of some number to the nth power, where n is even. Okay, so we're talking square root of something squared, the fourth root of something to the fourth, sixth root of something to the sixth, etc. is not just a. All right, it's not always just a, because again, what if a is negative? This symbol with an even root, an even index, is asking me for the non-negative nth root. So just to ensure that it is non-negative, we pop little absolute value symbols around. All right, so please know this rule right here for even roots. All right, so the nth root of a to the nth is not a, but the absolute value of a, something to ensure that we get a non-negative root, a non-negative result. Okay. All right, so now the odd roots, the easy ones are the odd roots. Remember I said this last video, every real number has exactly one odd root. Right? Every positive number, every negative number, 0, have, you know, 1 cube root, 1 fifth root, 1 seventh root. Well, I should say real, have exactly one real odd root. So let's take a look at those. All right, so again, keep this in mind for the even roots, and we're going to talk about the odd roots now. All right. So I'll just go through a few examples. So if I had the cube root of, let's say, 4 cubed. I'm writing things in this form here where I have the nth root of some number to the nth power. Right? The power inside here is exactly the same as the index, but this time it's an odd number, right? 3, 5, 7, 9. Right? Here it's 3. Well, if you roll through, right, this is the cube root of what's 4 times 4 times 4. That would be 64. And, again, what you're asked for here is the principal cube root. What's a real number that when raised to the third power gives me 64? Well, we saw it here, that's 4 to the third power. So 4 is the cube root of 64. And look, see how it's, cube root of 4 to the third, the cube root and the third power here, you basically can kind of say they undo one another, and you're just left with 4. Great. What about the cube root of, instead of 4 cubed, how about negative 4 cubed? Well, let's go through it. Right? What is the cube root of, what is negative 4 times negative 4 times negative 4? Well, a negative number to an odd power will end up being negative. Right? This is negative 64. And this is fine, right? We saw this in the last video as well, my evaluating nth roots video. You can take an odd root of any number, right? So just because there's a negative radicand doesn't mean this isn't real, right? If it was the square root or the fourth root, some even root of a negative number, that would not be a real number. But this is an odd root. And odd roots of negative numbers are just other negative real numbers. What number to the third power is negative 64? Well, we saw that earlier. That's negative 4. And this will go on, so see when, basically again, my cube root and my third power undid one another, and I'm left with just the base, just negative 4. So the way you would like things to happen, that didn't work out with even roots, the way that you would like things to work out actually does with odd roots, right? So it's the same for the fifth root, the seventh root. I'm not going to do any more of those. So I'll write the general rule here as well on this same page. So in general, you take the nth root of some number to that same power, to the nth power in the radicand, where n is odd, okay, cube root, fifth root, seventh root, ninth root, etc. This works the way you want. the nth root and nth power basically just undo one another, and you can just say, oh, this is equal to just a, and there's no need for the absolute value. An odd root can be negative, right? You saw that here. Here's an odd root, a cube root that ended up being a negative number. But when you are doing even roots, right, I'll say it one more time, when you see the symbol with an even root, an even index, your final result can't be negative, right? But it can be with odd roots, as I've said before. All right, so get these in your head, these two rules right here. All right, now keeping that in mind, let me move on to some examples. All right. So my first example, and you just really have to pay attention. Do I have an even index? Are these even numbers here? Or do I have an odd index? Right. Okay, so keeping those off to the side, here is my first example. I did this one already. Don't know why I must have accidentally, I forgot I had it later. I apologize. But we've already seen this, right? Again, just I'm going to point out what to pay attention to, right? This is an even index, right? That is the fourth root of, and then 5 to the fourth. It looks exactly like this, where the a is 5 and the n's are 4. Alright, so technically we can say that this is then equal to the absolute value of 5, right? But 5 is already a non-negative number, so there's no need for the absolute value around it, right? What is the absolute value of 5? That is simply the number 5, right? So there's the value that we're looking for, right? The fourth root of 5 to the fourth is just 5. Right? And again, we saw this example earlier. Okay, well, no, so far I've had a bunch of examples with a bunch of numbers, but that's not always the case. You might have variables, right? Here's another one. Let me get rid of this other one here. Here I'm taking the sixth root, right? You got the index of 6 of z to the 6, right? Where z is just some variable. I mean, so this is no different than this, right? Where instead of a, I have z, and the n's are replaced by 6. But pay attention, right? This is the reason, again, the reason I pointed to this one is because my index is even, right? It's a multiple of 2, sixth root. Okay, so the way I would simplify this, the sixth root of z to the 6, again, you can't just undo them. You can't just say it's z. And here's why not, right? This would be wrong. If I just left it this way, this would be wrong. This would be incorrect. And let's see why. All right, because remember, when you say two things are equal and there are variables involved, that means that they should have the same value for every value in the domain. Every number I can plug in for z should make this a true statement. So let's say I said this. Let's say, I made the mistake and I just undid the 6's and the sixth root and said it was just z. Let's check. What if z were a negative number? What if z were negative 1? Well, then the left side, you'd have the sixth root of, negative 1 to the 6th. And on the right side, you're replacing z with negative 1. All right, well, what is negative 1 to the 6th? Well, again, that's a negative number to an even power, so this would be positive. This would be positive 1. So this left side is the sixth root of 1. The right side is still just negative 1. And remember, I've said this a bunch now. When you see this radical symbol and there is an even index, what you're asked for is the non-negative sixth root of 1. So what's the non-negative number that when raised to the 6th power gives me 1? That would just be 1 itself, positive 1. That's not negative. And what we end up with here is, when I plug in negative 1 for z here and here, I'm getting 1 equals negative 1. That is false, right? That's wrong. Right? So what my statement set up here is wrong. Right? If you just undo the roots and the powers, right? Say it's just z, the sixth root and the 6th power undo each other. So that's why we have to ensure that the other side, because again, when I see this symbol and there's an even root, the other side better be non-negative. So the correct way would be to say that the sixth root of z to the sixth is, not just z, but the absolute value of z. Okay, and this is correct. Right, because try -1 now, right? When I replace z with -1, the left side would be 1, the right side would be the absolute value of -1, which is again 1. You get 1 equals 1, that's a true statement. And it'll work for any value of z. Plug in anything for z, this statement is going to be a true statement. Okay, so don't forget, if that expression on the other side can be negative, you're wrong, right? Put absolute values around it to ensure that it's non-negative. Okay. All right, my next example, finally dealing with an odd root. All right, here's the seventh root. The seventh root of 3x minus 2, right? So this 3x minus 2 is like the a, and then the 7s are the n's, right? And the reason I'm pointing down here is because now we're finally dealing with the situation where my index is odd, right? I'm taking an odd root. All right, so in that case, it's easy, right? When you have an odd root, you don't have to worry about if things are positive or non-negative or whatever. Just looking down here, when you take an odd root of some number to that same odd power, then you can think of these root and power as undoing one another, and you're left with just the base itself. So the seventh root of 3x minus 2 to the seventh power is just going to be equal to 3x minus 2. And that's it. I'm done. I'll box that in or something. All right. And if you want to test it out, you can test it out with a few values. If this expression truly is equal to 3x minus 2, then they should be equal no matter what I plug in for x, right? This should be a true statement. So what if nice one would be, if x were 0, that's an easy one. This side I'd have the seventh root of, 3 times 0 minus 2 to the seventh power equals, and then this side I'd have, 3 times 0 minus 2. This would just be the seventh root of -2, right? 0 minus 2. -2 to the seventh equals, and over here is just -2. And, -2 to the seventh, that's the seventh root of -128. Right? Again, negative number to an odd power is negative. Right? And 2 to the seventh is 128. All right. And is this equal to -2? Yes, you'd have -2. -2 to the seventh we just saw is -128. So this side is -2. This side is -2. Yes, that is true. Right? It works, and you'll see. And go ahead, try other values. You can do this all day long. Keep going. Plug in 1, plug in 10, plug in 1,000,000, plug in 1/3. Plug in whatever you want for x. And this will be a true statement. And there was no need for absolute values because the odd root, right, an odd root of a number can be negative, right? So this side over here, this expression over here can take on a negative value, like -2. All right. And I've just got a couple more here for you with, back to numbers. Back to numbers. All right, so here's one where, again, a very common mistake is made. I have the eighth root of -2 to the eighth power, and again the common mistake is to say that this is just -2. Oh, there's an eighth root and an eighth power. Those undo one another, and I'm left with just the base, just -2. Remember, again, I'm saying this again. When you see this symbol and there's an even number in the index, an even root, the final result, what you're being asked for, is the non-negative, not negative square root, or eighth root, sorry. So again, you can undo them and then just make sure it's positive, make sure it's non-negative by, it'll take the absolute value of -2. And again, this is going through this rule right here, where the value of n is 8, and the value of a is the -2, right? The base on the power of 8. And what is the absolute value of -2? That is simply +2, right? So the value of that expression is +2. Great, not -2. All right, and finally, I have one more for you. So again, let's pay attention to the index. Now, this is not written the way this is or this is, right? But I still have, I'm going to try to write it that way though, right? So here we have again, odd power, odd index. So I'm working with this, I'm going to try to work with this statement down here. Now, right now, this is the 5th root of a fraction, right? -32 243rds, right? Negative, 32 over 243. That's the radicand. I'm going to try to rewrite this radicand so that we have it written as a number to that 5th power. I'm going to try to rewrite this so it looks like this. And if you know what your perfect 5th powers are, I talked about perfect nth powers in the last video as well on evaluating nth roots. 32 is a perfect 5th power, right? That's actually 2 to the 5th. And 243 is also a perfect 5th power. It's actually 3 to the 5th. So if you'd like, I'm going to rewrite this as the 5th root of, and then what's a fraction, what's a number that I can raise to the 5th power, right? So I'm going to put something to the 5th power in here, just like down here. And I'm looking for that a, right? What's a number that I can raise to the 5th power to give me negative, 32 243rds? And I already mentioned it. Well, first of all, it'll be negative, right? Because a negative number to an odd power will give me another negative number. And I've mentioned that, 2 to the 5th, so 2 in the numerator, 2 to the 5th will give me 32 in the numerator there. And then 3 to the 5th is 243, right? So 3 in the denominator to the 5th will give me the 243 in the denominator. All right, so now I have exactly like this form down here, where the value of n is 5, the value of a is this fraction, the base on the 5 here is this -2/3. And when it's an odd root, you don't have to worry about, is my result positive or negative or non-negative? The result can be anything when you're taking an odd root. It can be positive, it can be negative, it can be 0. So 5th root of this number to the 5th power, the root and the power kind of just undo one another, and this is simply -2/3. And that's it. No absolute value. It is negative, and that is fine because we have an odd root. All right, so please keep these rules in mind. Try to put them on some flashcards or something and get to learning them. They don't come up too often, but they are very useful in the simplifying of roots that we're going to do in later sections, later videos. All right. So as I like to say at the end of these videos, try the best you can to learn the material on your own before you go looking for help. Because I find that people who take the time and the effort to learn material on their own tend to remember the material better and for longer. So read the material, of course. Read through the author's examples. Perhaps even try to work out the solutions to some examples before you read how the author did it, and then compare your work to the author's and see if you can learn from some mistakes there. Obviously, work on plenty of exercises and practice problems, and look up solutions whenever they're made available to you, just to check how you're doing. And don't just give up after one attempt at a problem. Very often in mathematics, there are several approaches that'll work for any given problem. But if so after several attempts, several approaches at a problem, if you're still not getting it, then perhaps you should try to read the material one more time, maybe even a third time, more slowly, deliberately. Take notes. Because if you've done some problems or tried working on some, chances are you have a better idea as to what the author expects from you, what the author wants from you. So you'll also have a better idea as to what to look out for when you're reading the material. So a second read-through, a third read-through, could shed some light on some of the subject that you didn't see before and make working on the problems that much easier. But if after that, if after several read-throughs of the material and several approaches of problems, you're still not getting it, it is not a sign of weakness whatsoever to go looking for help. That is what other people are there for, to help. So ask a teacher, a tutor, a friend, someone who you know in the class that knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's loads of those out there too, such as this one, or tons of them out there that I'm sure are better than mine. I assure you can find them very easily. But just keep at it. Keep practicing, stay persistent, don't give up. And I think the hardest part too is to try to maintain a positive attitude about a subject. You know, try to stay focused and motivated and positive. Keep thinking that you're going to enjoy something, that you're going to take something away from it, and find meaning and reason for what you're doing if you can, and try to have fun with it. I know that's easier said than done. Some of you, if you think that it's going to be dull and boring and you're going to hate it, well, that's what's going to happen. All right. So it's amazing how a change in mindset, a simple change in attitude, can make a huge difference in the learning experience. So stay positive, please. Keep practicing, stay persistent, and just don't give up. Don't give up. And I just know you can get it. All right, and thank you very much for watching.